Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 19 on more ODEs.
In this lesson, we'll consider some new families of ordinary differential equations, their solutions, and what they're good for. Along the way, we'll learn some new methods and some new applications.
Among the many differential equations that you may encounter, a few families are worthy of note. Some ODEs are autonomous, meaning that the right-hand side depends on x alone and does not depend on t. Those equations that do depend on t are called non-autonomous equations. They can be very difficult to solve. Some, however, are solvable by the following separation method. If dx dt is of the form of a function of x alone times a function of t alone, then, following the pattern of what we did for the linear differential equation, we can separate out all of the x terms on the left, all of the t terms on the right. Then it makes sense to integrate both sides if these integrals are computable, and if you can solve for x, then you're in good shape. Let's look at an example. If you consider a body that is falling under the action of gravity, you'll notice different behavior depending on its shape. This is due to drag force. If we assume a drag force model where that force is proportional to the velocity of the body, then what do we have? Well, our body is being acted on by a gravitational force of magnitude m, the mass, times g, the gravitation constant, pointed down. Pointed upwards is the drag force that is assumed proportional to the velocity v by some constant of proportionality, kappa, the drag coefficient. Newton's law says that the mass times the acceleration, dv dt, is equal to mg minus kappa times v. And here we have an autonomous and separable ordinary differential equation. By doing a little bit of factoring and algebra, we can move to the left-hand side the quantity v minus mg over kappa, all in the denominator. On the right-hand side, what is left over is negative kappa divided by m dt. Integrating both sides, what do we do? Well, on the left, you have to think a moment to see that the antiderivative of dv over v minus a constant is in fact the log of quantity v minus that constant. On the right-hand side, the integral is very easy. It is negative kappa over m times t. We'll put our constant of integration on the right side. Now, to solve for v, what do? We exponentiate both sides. On the left, we have v minus mg over kappa. On the right, we have e to the negative kappa over m times t. That's times e to the constant of integration. We're just going to call that a new constant with the same name, c. Now, solving for v, what do we have? V is constant e to the negative kappa over mt plus mg over kappa. Let's think about this for a moment. If we take a limit as t goes to infinity, what happens? Well, the exponent in the exponential is negative. That means that term goes to 0, and goes to 0 rapidly. What remains is a constant velocity equal to m times g over kappa. This is called the terminal velocity. Depending on the value of kappa, it may be very fast or rather slow. Separable ODEs also arise in analysis of a fluid leaking from a tank. This is regulated by Torricelli's law, which relates h, the height of the liquid, with a, the cross-sectional area at the top. the law states that the rate of change of h with respect to t is proportional to the square root of h and inversely proportional to a. If we consider, say, a cone or anything where the cross-sectional area is quadratic in h by some constant, maybe pi, maybe not, then we obtain h prime is proportional to h to the negative 3/2. This is separable, and moving the h to the 3/2 over to the left side and then integrating both sides yields on the left h to the 5/2 times 2/5, and on the right a constant times t plus an integration constant. Solving for h gives a linear function of t raised to the 2/5 power, where the constants will depend on the physics in your initial condition. What this implies is that h approaches 0 very rapidly at the end. How rapidly? It is in big O of the final time minus t raised to the 2/5 power. That comes into 0 very, very sharply when you're looking at something to a power of 2/5. Let's move on to a different class of non-autonomous ODEs. These are the linear non-autonomous ODEs. They're of the form dx dt equals a of t times x plus b of t, where a and b are functions of t. For example, dx dt equals tx plus 1/2 t squared is of this form. We say that it's a linear equation because if you suppress the t dependence, you get something of the form dx dt equals ax plus b. And that right-hand side should remind you of the equation of a line. Well, how do we solve such a problem? The method that we will introduce is that of the integrating factor. It's a little tricky, so hang on. Let us denote that integrating factor by I. We're going to multiply both sides of this equation by an as yet unknown function I. Rearranging terms a little bit and multiplying through gives us I times dx dt minus ai times x, and on the right, I times b. Now, what is this good for? Well, if you look at that left-hand side and keep in mind the product rule, then you see something that should remind you a little bit of the product rule. If we had something that looked like I times dx dt plus di dt times x, well then, we would recognize that that's just the derivative of I times x. And that's something that's going to be helpful to us. So what would we need to be true in order to have this? We would need to have di dt equal to negative a times I. Now, focus on that, because what we're doing is deriving a differential equation for this unknown integrating factor I. That is separable. That is solvable by the standard techniques that we've been using. When we solve that equation, what are we going to get? I is e to the integral of negative a dt, which we could write in shorthand as e to the negative integral a. If we choose such a function, I, and multiply both sides of our original equation by this, then what we obtain is on the left, the derivative of I times x. On the right, I times b. Now we can integrate both sides, because differentiation and integration undo each other. On the left, we have I times x. On the right, the integral of I times b. We can solve for x and obtain, after substituting in our formula for I, a scary looking but very useful equation. The solution is x is e to the integral of a times the integral of b times e to the negative integral of a. Let's demonstrate this formula in the context of a mixing problem. Assume you have a tank that holds 1,000 gallons and is 90% full. An additive is injected at a rate of 10 gallons per minute. The solution is mixed well and then drained out at a rate of 5 gallons per minute. The question is, what is the concentration of the additive at that moment when the tank is full? There are a couple of features to this problem we're going to have to analyze. First of all, we're talking about when the tank is full, so we've got to be concerned with volume. Also, we are told the rate of change of the volume, that coming in and that going out. Lastly, what we're asked about is the concentration of the additive in the tank. Let's set a few variables. First of all, V as a function of t is our volume. Next comes Q of t. That's the quantity of the additive that is put into the tank. So that when we talk about the concentration, C of t, that is simply Q of t over V of t. Let's derive the differential equation and then solve it. By considering flow rates coming in and out, it's easy to see that the volume is the initial volume, 900, plus 5t, meaning that the tank will be full at precisely t equals 20. If we consider the time rate of change of the amount of additive, Q, well, that additive comes in at a rate of 10 gallons per minute, but the fluid is drained out at a rate of 5 gallons per minute. That drained out fluid is not pure additive, but depends on the concentration, C. Thus, we derive a differential equation on Q as follows: dq dt plus Q over 180 plus t equals 10. This is a linear, non-autonomous ODE, where the function a is negative 1 over 180 plus t. That means our integrating factor is e to the integral of dt over 180 plus t. Of course, that integral is simply the log of 180 plus t, and when we exponentiate that, we obtain simply 180 plus t. If we therefore multiply the differential equation by this integrating factor, we obtain, very simply, 180 plus t times dq dt plus q equals 10 times quantity, 180 plus t. The left-hand side is the derivative of q times quantity, 180 plus t. Integrating both sides gives us on the left 180 plus t times q, on the right 1800t plus 5t squared plus a constant. You can show, based on the initial condition that there's no additive at the beginning, that that integration constant is 0. Now we almost have the solution to our problem. What do we need to do? We solve for q as 1800t plus 5t squared over 180 plus t. But we're asked about the concentration at the time when the tank is full. At t equals 20, we get the amount of additive to be 190. Therefore, the concentration at that time is 190 divided by the volume of the tank. That means that the additive is present at 19% when the tank is full. There are many similar types of problems for which integrating factors are helpful. Some of them are like this, involving mixing and tanks. Others come from entirely different applications. Indeed, this is just the beginning of the wonderful subject of differential equations, where there are many more families of differential equations that require specialized solutions. A few of these are doable with the tools that you now have in hand. But many of these differential equations require multivariable calculus. Some can be very difficult to solve indeed.
We now have in hand several types of ODEs, their solutions, and their applications. That's the good news. The bad news is most differential equations are hard to solve. Some seem impossible. In our next lesson, we'll consider what to do when the solution seems to slip from our grasp.